So this is number 3 from the 2011 AP Calc AB exam, and they describe a region in the coordinate plane bounded by the graph of 8x cubed and sine of pi x. They've given us the region. They were even nice enough to provide us with the intersection of the two curves. So one of the intersections is 0, 0. The other intersection is 1 half, comma 1. And then what they want us to do in part A is write an equation for the line tangent to the graph of f at x equals 1 half. So f is the cubic, so if you think about it, the cubic is going to be the one that looks like this, and then this is the one that kind of comes up and changes direction. So if we had it continue to graph, it would produce the sine wave. So here's the graph of f of x, and we want to know what an equation for the tangent line is to f of x at 1 half. So the slope of that tangent line is going to correspond to the derivative of f evaluated at 1 half. Pretty simple derivative to take. You need to evaluate that derivative at 1 half, so if you do that carefully, you get a slope of 6, or a derivative value of 6. And then the point of tangency is going to be 1 half comma f of 1 half, and if you use this formula to find f of 1 half, put 1 half in place of x and cube it, you get 1/8. 8 times 1/8 gives you a y value of 1. And I guess we also could have looked at the graph here to conclude that our point of tangency was going to have an x value of 1 half and a y value of 1. If you use point slope form for your tangent line, you're going to have y minus y1, which is here, equals m times the quantity x minus, and there's your x1. Slope intercept form obviously also would have been totally fine. Part B of this is the toughest part. It involves the most work. It has the most places where things can go wrong. It wants the area of your region. So the area of this region, if you take a slice of it vertically, the top of every vertical slice is going to be on the graph of g of x, and the bottom of every vertical slice is going to be on the graph of f of x. So I took my vertical slice, and then I realized that this dimension, the height of my vertical slice, was going to be a difference in y values. I need to take the bigger y value, which is on the graph of g of x, minus the smaller y value from the graph of f. So I had g of x minus f of x, and then the width of that tiny thin slice is going to be delta x. So the area of one slice, if we approximate it to be a rectangle, can be found by taking this times delta x. If we want to add together an infinite number of those slices' areas, the definite integral will do all the work for us. So we integrate this expression from 0 to 1 half, because all vertical slices that we could have taken within this region are going to range between 0 and 1 half with their x values. And then to take this integral, split it into two pieces, because you have a piece that's going to be a little more straightforward than the other part. This is the part that's a little bit simpler, because taking the antiderivative of this just leaves you here, and then it's not very difficult to simplify that, plug in your limits of integration, and take a difference. The integral over here, though, since you have this inner function, is going to require a quick u substitution. So you let u equal the inner function, compute du dx, and then you're going to have to put du over pi in place of the dx. So you pick up this 1 over pi, and then if you take the antiderivative of sine, you're going to end up with negative cosine. So here's the constant we picked up. There's the negative from the antiderivative of sine being negative cosine. I've given myself these little reminders here because I did not change these to u values. These are x values. So I need to make sure that I only put these numbers in place of x. I can't put them in place of u. So before I put 1 half and 0 here, I have to make sure that I get x back in place of u. So pi of x is going to replace u. And then on the next screen, I'm finally going to be ready to put in my limits of integration and take a difference. So if we look at that, we end up with 1 half going in place of the x in this expression. We end up with 0 going in place of the x in this expression. And if you simplify, it ends up being cosine of pi by 2 here, cosine of 0 there. Well, the cosine of pi by 2 at this point on the unit circle, the x-coordinate, or the cosine of this angle, is going to end up being 0. So this term drops out completely. This piece is going to stick around because cosine of 0 is 1, the x-coordinate of this point on the unit circle. So we have, minus a negative, or positive 1 over pi times 1. And then from the previous screen, if we raise 1 half to the 4th power, we're looking at this. 2 times 1/16 is going to give you 1/8. And then this would be the area between your two curves. So pretty tiny value. And in part C, we're asked to do a little bit more with volume this time around. So we take this region, we rotate this region about the horizontal line y equals 1. And what we end up generating as we rotate this entire region is kind of an odd shape. But if you visualize just the slice being rotated about y equals 1, you have this gap in between the slice and the axis of rotation. And so what's going to get traced out by the slice being rotated about y equals 1 is going to be a washer. And the outer radius is going to go from the axis of rotation to the far edge of your slice. Now that's a difference in y values. If you want to specify it to be positive, you need to take the bigger y value, which is 1, minus the smaller y value at the bottom of your slice, which is on f of x, or 8x cubed. So there's the big radius. The small radius comes from this gap in the solid, or in the coordinate plane between the axis of rotation and the top of our slice. And that's a difference in y values as well. And the bigger y value is still 1. Smaller y value is now on the top curve, or sine of pi x. So we have our big radius, we have our small radius. To find the area of the face of the washer, we'll do the area of the outer circle minus the area of the inner circle. So I have pi big R squared minus pi little r squared. The volume of the washer is going to be the area of the face times the third dimension, the tiny little bit of thickness that this has, which is delta x, same as the width of our slice in the coordinate plane. And then if we want to add together many of these washers' volumes, we're going to have to use the definite integral to make that happen. And so we integrate this expression here, the delta x becomes a dx, and then the limits of integration have to be the x values, since this is a dx, our integrals with respect to x, and our limits of integration have to be the x values that all possible slices could have ranged between, and that's still going to be between 0 and 1/2, just like it was in part A.